Okay, guys, today we will talk about the lecture 4 hash functions based on block ciphers and the modular arithmetic. We move from general properties and the constructions to specific hash functions is now made, and in this lecture, the subclasses of unkeyed hash functions, known as modification detection codes (MDCs), is considered. From a structural viewpoint, this may be categorized based on the nature of the operations comprising their internal compression functions. From this viewpoint, the three broadest categories of iterated hash functions studied to date are hash functions based on block ciphers, customized hash functions, and hash functions based on modular arithmetic. Customized hash functions are those designed specifically for hashing with speed in mind and independent of other system subcomponents. For example, block ciphers or modular multiplication subcomponents, which may already be present for non-hashing purposes. In this table, you can see the conjectured security of a subject of the MVC subsequently discussed in this lecture, similar to the case of block ciphers for encryption, for example, 8 or 12 round DES or 16 round DES. Security of MDCs often comes at the expense of speed, and the trade-offs are typically made. In the particular case of block cipher based on MDCs, a provably secure scheme of Merkle with rate 0.276 is known but a little used, while MDC2 is widely believed to be secure. This MDC2 has rate 0.5 and receives much greater attention in practice. What about the hash functions based on block ciphers? A practical motivation for constructing hash functions from block ciphers is that if an efficient implementation of a block cipher is already available within a system, either in hardware or software, then using it as a central component for hash functions may provide the later functionality at little additional cost. Here in this slide, you can see the table. This table shows you upper bounds on strength of selected hash functions and n-bit messages, and it's the bit size. N-bit message blocks are processed to procedure m-bit hash values. Number of cipher or compression functions operations currently believe it necessary to find pre-images, and the collisions are specified, assuming no underlying weaknesses for block ciphers. Here, figures for MDC2 and MDC4 account for DES complementation and the weak key properties. Regarding rate, you can see this in the definitions later. Here, if you look at the table, here you can see the hash functions. It's the Meyer MDC2 with this, MDC4 with this, Merkle with this, MD4, MD5, SHA1, and RIP-MD 128. Here the n it's our bit size. Here in the MDC2 we use 64, in the MDC4 also 64, in Merkle 106, in the MDC4 512, in the MDC5 it's the same with the MDC4, and for the RIP-MD 128 it's the 512 bit size, and m here our hash value for all the unkeyed hash functions is the same, except CHA1, it's the 160, and also we can see the size of the pre-image. Here for the MDCs it's the 82 degree of 2, for the MDC4 it's the 109 degree of 2, for the Merkle it's the 112 degree of 2, For the MD4, it's the 128 degree of 2. For the MD5 and the RIP MD 128, it's the same. And for the SHA1, it's the 160 degree of 2. If you look at this column of the table pre-image, you can see that the degree of the degree of the 2 is the same with the hash value for the MD4, MD5, and this RIP MD 128 and the SHA1 hash functions. For the collision, we have this kind of values. You can see here it's the for the MDC to 54 degrees of 2, and for the Merkel it's the 56 degree of 2, and etc. Here here for this column, we also see the comments column here. For this Myers hash function, we use bit size n as a k-length. For the MDC2, rate will be the 0.5. For the MDC4, rate will be the 0.25. For the Merkel, rate will be the 0.276. And for the MD4 and the MD5, we will talk later. And here, for the Meyer hash functions and MDC2 hash functions, you can see the symbols A and B. A means that the same strength is conjectured for Davis-Meyer and the Prenel hash functions. For the B symbol, it means that strength could be increased using a cipher with k length equal to cipher block length. Here, the hope is that a good block cipher may serve as a building block for the creation of hash functions with properties suitable for various applications. Constructions for hash functions have been given which are probably secure, assuming certain ideal properties of the underlying block cipher. However, block ciphers do not possess the properties of random functions. For example, they are invertible. Moreover, in practice, block ciphers typically exhibit additional regulations or weaknesses. For example, for a block cipher, for the block cipher E, double encryption using an encrypt and decrypt cascade with k parameterized 1, k parameterized by 2 results in the identity mapping when k1 equal to k2. In summary, while various necessary conditions are known, it's unclear exactly what requirements of a block cipher are sufficient to construct a secure hash functions and properties adequate for a block cipher. For example, resistance to chosen text attack may not guarantee a good hash functions. In the constructions which follow in the definition that we use here, first definition that the block cipher is a block cipher defining an invertible function from n-bit plain text to n-bit ciphertext using a r-bit key. If E is such a cipher, then E parameterized by k from x denotes the encryption of x and the key k. Discussion of hash functions constructed from n-bit block ciphers is divided between those producing single lengths n-bit and the double lengths 2 n-bit hash values, where single and the double are relative to the size of the block cipher output. Under the assumption that computations of 64 degree of 2 operations are infeasible, the objectives of single length hash functions is to provide one-way hash functions for ciphers of block lengths nearly n equal to 64. It's our bit size. Or to provide collision resistance hash functions for cipher block lengths nearly n equal to 128. The motivation of double length